Good afternoon, everyone. I'm Alhasan, a last year PhD student in the Department of Physics. My research focuses on investigating the role of green hydrogen in decarbonizing the New Zealand heavy transport and overall the role of green hydrogen in New Zealand national energy system. So we have simulated, previously we have simulated the role of hydrogen vehicles in decarbonizing the New Zealand heavy transport. We then investigating the trade-off between hydrogen and battery electric vehicles. So as part of our research, we then done an optimization model in order to optimize the placement of hydrogen refueling stations. So hydrogen trucks are promising for decarbonizing the heavy vehicles, specifically for the long-haul heavy trucks. But the early hydrogen rollout is expensive and extremely risky. So why is that? Because the first thing is that the lack of hydrogen stations is impacting the uptake of hydrogen vehicles. Why is that? Because if there's not enough hydrogen stations, so that will increase the range anxiety and the downtime, and also will increase the detours to find the nearest refueling station. So that will negatively impact consumers and manufacturers' decision in order to rely on this technology, which then impact infrastructure providers. So they will not invest in this technology because it's unreliable, which then negatively impact consumer and manufacturers as well. So this is one side of hydrogen refueling stations. In contrast, having too many or placing hydrogen stations in wrong places is another issue. So that because having too many stations or place them in wrong places, it may increase the risk of making these stations underutilized, so that make them economically unsustainable. For example, then they will shut down. For example, these days, in many countries such as Austria, Germany, California as well, they have started shutting down lots of hydrogen stations. I would like to clarify that this is for hydrogen passenger vehicles, not heavy trucks. Heavy trucks are more based on known roads, but it's better to learn from this lesson. So we have two main issues. The lack of infrastructure, or even having too many structure, is even another issue. So shutting down the stations will impact infrastructure providers and also negatively impact consumer and manufacturers as well, which I guess making the problem even worse. So how to know? So it's the best option is to know how many stations are needed to cover the projected demand, where to place these stations, and when. So that led us to the research objective. So the objective of this research is to answer this important question: how many hydrogen stations are needed to cover or supply the New Zealand heavy transport, hydrogen vehicles, and where to place these stations and when. So we developed an optimized demand-driven station rollout for hydrogen heavy-duty vehicles, for the aim to have the right number to cover the expected growth and the right place and the right time based on annual basis. So what we have done, so we have specified, we separately simulated the New Zealand, the South and the North Island. So we specify 20 potential location places in the South Island and 29 places in the North Island. This is an example, the places that we chosen for the South Island. Try to cover the main cities and nodes and high roads. So we define the traffic volumes in all these places. For example, based on the current fleet, Christchurch is almost 11% of the traffic volume, while Nelson about 10%. Then, we also define the distances between all these places as a matrix. the vehicle assumptions, because we are focusing on the long haul heavy vehicles more than 20 tons. So the average travel distance, the annual average travel distance is 63 kilometer per year. And the vehicle tank size is 40 kilogram. And the fuel economy improves linearly from 2025 to 2050, meaning that the range is increasing over time. So these are the main assumptions, assuming that the dispenser refueling rate is 216 kilogram per hour, assuming that we have 2 dispenser per station, and the station operates the station operate about 80%, meaning 20 hours a day, and the overall target utilization is 10%. That to reflect the current conventional fleet. So the fleet uptake is the simulation period is from 2025 until 2050, and we are defining the uptake using a modified sigmoid curve. So we simulated 2 different scenarios or models. So in the first model, we could see it's a simplified model. So in this model, we are assuming that the uptake of hydrogen vehicles is distributed throughout the whole island. So yeah, I'd like to mention that the model is dynamic. So I mean, we are not assuming that we have fixed number of hydrogen stations per year. No, so the model based on the fleet uptake, the model calculate how much hydrogen stations are needed. So the model is dynamically calculate demand and provide these stations. So yeah, in the first model, assuming that hydrogen heavy vehicles are distributed throughout the whole island, then for each candidate site, the model calculate the average travel distance and then locates the station in the place that minimizes the average travel distance. So the key findings, the first model for the South Island. So the first station is located in Ashburton. So this circle so we're assuming that each hydrogen station is covering the vehicles within the third of the vehicle range, because assuming a 30% as buffer. So in order to guarantee a round trip. So for example, hydrogen station in Ashburton will cover the other vehicles within this range. So this is the place of Ashburton, the first station in Ashburton, the second station in Gore, the third one in Plenum. As that because based on the assumptions that the uptake of hydrogen stations is distributed in the whole island. So we see that the stations are widely distributed. This is, for example, the fourth and the fifth one. So this is a simplified model. And this shows how the average travel distance decreases with the increase of hydrogen stations. This equation is very beneficial. It can give us, it can be used, for example, based on the number of hydrogen stations, how could the average distance be decreased? And we use this in our model as well. So yeah, the key message is that we see that this optimization give a fast distance reduction is observed, but here there's a risk increasing the risk of low utilization. Because, for example, here we are each time we are creating new hubs. So, for example, the first station in Ashburton, the second one in Gore, the third one in Plenum, but maybe the uptake is not enough. So that will not make these stations economically sustainable. So, based on the previous case that some countries are now shutting down hydrogen stations. So that may, I'm not saying that it's not correct, but maybe increase the risk of shutting down these stations. So, this is the North Island, the first station in Hamilton, then Auckland, then Palmerston North, and then Pariwa and Manurua and Toriko. I'd like to mention, same behavior is observed, but because here the North Island is denser than the South Island, we see that so many stations are located in this area. So this is the current hydrogen refueling stations by Heringa. So the red dots are the current stations that are in operation. So you see that the model the first 6 stations suggested by the model include these 4 stations that are currently in operation. But yeah, on the other hand, the second model, okay, we said that that model is oversimplified. But in reality, hydrogen stations, the uptake will not just be distributed over the country. Once we have a hydrogen station, then it's more likely that the uptake will be clustering around this station. Then with the higher uptake, another station will be located within this area. Then we have a smooth distribution of the uptake on hydrogen stations as well. So in order to reflect this clustering, we added a factor to weight the traffic volume nearby existing stations, a factor alpha. So we still have the same objective to minimize the average travel distance, but we are more weighted the traffic volumes nearby any existing stations. So the results, so the first station is in Ashburton, but as mentioned that, so this, we will expect higher uptake in Ashburton and nearby cities. So yeah, I mean, this is the first model. We see that they are widely distributed. But in the second case, we see that the first one is in Ashburton, but the second one is in Christchurch because we have higher uptake. Then while fleet uptake growth, another station will be within this area because that in order to reflect reality, the third one in Timaru, then Umaru, then Dunedin, then Rays Junction. So I don't want to say that this is wrong, this is correct, but it's just to see the consequences of each one, and so that depends on the policy. And so we can see that the first model, this rolling out of hydrogen stations may increase the risk of the station being underutilized, while this one could be more realistic, makes them economically more sustainable. Same for the North Island. This is in the first model, while the second model, we see that the hydrogen stations are placed in these dense areas, then it's jumped to create new hubs after a long time. So this shows the coverage of hydrogen station, how much of the traffic volume is covered by these stations. We see that the second model coverage more of the traffic volume than the model one, because it's just distributing the stations throughout the island, but it could be not realistic. So model one could be policy driven. For example, if the government just want to say, okay, we want more than 80% of the traffic volume need to be covered by hydrogen stations in 2030 or something like this, what is the optimum way? So the model one is a good idea. But as I mentioned, that because these are economically driven, they need to at least achieve the minimum profit. Otherwise, they need more support by government or they will shut down. So we see that model 2 is more realistic. It's economically driven. And yeah, I mean, just as a sensitivity analysis, in order to show the importance of the first station, we see that what if we force the model to place the first station in Invercargill to see what else. So you see that the first one, Invercargill, Lumsden, Rays Junction, Dunedin, Oamaru. On the other hand, what else if the first station located in Nelson? Then we see Nelson, then Plenham, Kaikoura, Waibara, and Darfield. And this shows that coverage traffic volume based on these places. So the Pro one showed that if we just place the first station in Ashburton, so that in the first year it's covering almost 30% of the traffic volume, which is double than the case placing the station in Invercargill. Over time, we see that it's very interesting to see that between this, from 2030 to almost 2040, placing the station in Invercargill, it will cover most of the traffic volume for about 10 years, while we see that it's almost 42% placing this in Invercargill, and it's in between if we place them in Nelson. So we can see that the first station acts as an anchor for the next 10 or 15 years. So the main conclusion is that the dynamic optimization provides clear answer to the core question: how many stations are needed to cover the projected uptake, where and when to place them. It can be integrated in other dynamic modeling as a positive feedback. And then model one gives dispersed network distribution and it's rapidly distance reduction. The second one, it's more realistic as it's clustering around early hubs. Especially we see that North versus the South Island require different rollout given the different freight patterns. Early station placement strongly shapes the long-term network evolution. And we can see that this posted factor could be used as an indicator in order to see what is the best place, which one will be more economically viable. And this, because just by changing the main assumptions, it can be applied even in New Zealand or any other countries. So, I mean, this could be a good insight for stakeholders and policy decision makers. But I see that further development could be happen with collaborating with stakeholders, or even, I mean, if we also incorporate economic factors such as some places we can produce hydrogen cheaper than other cities. Incorporating this will significantly improve their results. Yeah, and at the end, I would like to thank the German and New Zealand grant supporting my scholarship, also the Hihonuka Hawaii, and that's all. Thank you very much.
Thank you, Hassan. Have we got time for a question?
Thank you very much. Great presentation. Just 1.5 questions, I would say. Was there any AI involved in here? And if not, or like yes, overall it looks like multi-parametric AI modeling. So
yeah, I mean it's open source Python. Then we just base some Python modeling is just assuming that a fixed number of hydrogen stations. So yeah, it's a Python code then developed to reflect the New Zealand context.
Hassan, hydrogen takes a fair amount of water and electricity. Did you think about that in terms of where you were placing them, whether they were near generation sites or near rivers or?
Could you say again, please?
Did you pay any attention to sources of water and electricity?
Yeah, so that I said this could be further development to incorporate economical aspects of placing hydrogen stations. Yeah.
Okay, thank you.
Okay, thank you.